In 2012, a team of scientists at the University of Auckland designed a test for one of the most cognitively demanding challenges they could construct. They placed food inside a clear tube, sealed it, and surrounded it with a series of tools. To retrieve the food, the subject had to reason backward. They had to look at the outcome they wanted, identify the specific cause that would produce it, and select the correct tool on the first attempt. The test was originally built for great apes. The subject in front of them was a parrot. It solved it. First try. And when the scientists reviewed the footage, what struck them was the stillness before the solution. The bird looked at the tube, looked at the tools, and moved with complete certainty. It already knew. Dr. Alex Taylor and his team had spent years studying causal reasoning, the ability to understand why something happens, as opposed to what happens next. Great apes possessed it. Crows had a partial version. Parrots, the research confirmed, possessed it in full. They could work backward from a desired result, identify the mechanism that would produce it, and act on that understanding without trial and error. Causal reasoning is one of the rarest cognitive abilities on the planet. It requires holding an imagined future in your mind, tracing a path back to the present, and selecting the correct action from a set of options that all look plausible on the surface. Most species never develop it at all. The parrot in that Auckland lab had it, used it without prompting, and moved on. But the Auckland study was only part of the picture. To understand what a parrot's brain is actually capable of, you have to go back further. Back to a gray parrot named Alex, a Harvard laboratory, and 30 years of work that changed what scientists believed about animal intelligence. Dr. Irene Pepperberg acquired Alex in 1977 from a pet store in Chicago. He was 1 year old. Over the following 3 decades, Pepperberg worked with Alex every single day, running structured sessions that probed the edges of what a non-human brain could understand. What emerged from that work rewrote the textbooks. Alex could identify more than 50 objects by name. He could sort them by color, material, and shape simultaneously. He understood the relational concepts of same and different well enough to apply them to objects he had never encountered before. He could count quantities up to 6. Without counting sequentially, he looked at a group of objects and simply knew how many were there. An ability called subitizing that human children develop around age 3. These results, on their own, were extraordinary. But the finding that stopped other scientists came in 2005. Pepperberg placed 2 identical objects in front of Alex and asked what was different about them. There was nothing different. Alex studied the objects, turned to Pepperberg, and said none. He produced the correct answer to a question about the absence of a difference. He understood 0. A concept arrived at on his own, the idea that something can be absent, and that the absence itself is a meaningful quantity. Human civilizations took thousands of years to formally develop 0 as a mathematical concept. Ancient Greece, for all its intellectual achievement, had no symbol for it. Alex produced it spontaneously during a laboratory session on an unremarkable afternoon in Cambridge, Massachusetts. What makes this possible lies within a piece of neural architecture that researchers were unaware of until a study published in PLOS One in 2015. When scientists examined parrot brains in detail, they found a structure surrounding the vocal learning core that appears in no other bird species on Earth. They called it the shell region. This shell is the dividing line between mimicry and genuine learning. Other birds produce sounds. Parrots acquire language. The shell enables what scientists call open-ended vocal learning, the ability to build new associations, new vocalizations, new conceptual links throughout an entire lifetime, rather than within a narrow developmental window in youth. Most animals have critical periods, windows in early life during which certain types of learning occur with extraordinary efficiency and then close permanently. A dog learns its name, its commands, its routines, and that largely holds. The circuitry for acquiring genuinely new things solidifies and stops expanding. Parrots have no such closing. A parrot at 40 years old can encounter a new word, a new object, a new problem structure, and integrate it fully into what it already knows. The window stays open until the bird dies. The mechanism driving that capacity turns out to be dopamine-driven feedback loops in the basal ganglia, the same circuitry that fires in the human brain when you master a new skill, acquire a second language, or finally grasp something you had been working to understand for weeks. When Alex learned a new concept, his brain activated in patterns that, to neuroscientists reviewing the data, looked almost identical to those of a young child learning to speak. The same reward architecture, the same reinforcement signal, the same loop of attempt, feedback, and consolidation. The difference between Alex and most other animals was that he never stopped triggering it. Every session, every new object, every question he had never been asked before, he engaged with all of it as though the loop was still hungry. Because it was. There is one detail from Pepperberg's research that tends to stand out from the rest. Alex did not only answer questions, he asked them. Pepperberg documented multiple instances across the 30 years of their work together in which Alex encountered an object he had no name for, turned to her without prompting, and asked what it was. He was generating a question from his own internal awareness of a gap. He had identified something he did not know, and he went after the information to fill in the gaps. That curiosity did not diminish with age, with routine, or with the enormous quantity of information he had already accumulated. Every day in that laboratory, Alex treated the world as though it still had things to reveal. Because it did. Macaws in the Amazon have been observed returning to clay licks, exposed riverbank faces rich in sodium and minerals for generations. The younger birds watch the older ones and learn which licks are safe, which are exposed to predators, and which require a certain angle of approach. But when a lick is destroyed by flooding or erosion, it is the birds that have maintained the habit of exploring new territory that locate replacements fastest. The ones that stopped exploring years ago are the ones that struggle. Exploration, for a parrot, does not switch off when the environment becomes familiar. It stays on, running quietly in the background, so that when the familiar ground disappears, the capacity to find new ground is still intact. Think about what happens to most people somewhere between childhood and adulthood. As a child, you asked questions constantly. You pointed at objects and demanded their names. You took things apart to see how they worked and felt no anxiety about the uncertainty that came before the answer. You tried things without strategy, without calculating the risk of being seen to fail, without needing to know the outcome before you began. Learning felt automatic, almost physical, a pull toward the unfamiliar rather than a retreat from it. You were, in the language of neuroscience, running your loop at full capacity. At some point, that changed. The questions became fewer. The instinct to figure something out from scratch gave way to the assumption that you probably already understood it well enough. The willingness to be visibly wrong in front of others got quietly replaced by a habit of staying inside what you already knew. The domains you engaged with narrowed. The problems you sought out became the ones you were already equipped to solve. And with each year of that narrowing, the loop got a little quieter, fed less often, triggered less reliably, requiring more activation energy to get moving at all. The neural architecture went nowhere. The basal ganglia, the dopamine loops, the reward signal that fires, when genuine understanding clicks into place, all of it is still running. What changed was the frequency with which you gave it something real to work on. Parrots in the wild face environments in constant flux. Fruit ripens in different locations at different times of year. Predators shift their patterns. Flock dynamics reorganize. Foraging grounds that sustained a population last season may be stripped bare this season by competition or drought. The birds that survive across decades are the ones that keep testing, keep updating, keep treating each new situation as data rather than a threat. Researchers studying wild parrot populations have found that cognitive flexibility, the willingness to try a new approach when an old one stops working, is one of the strongest predictors of survival across a long life. The birds that thrive are curious ones, the ones that investigate, the ones that approach novel objects rather than retreat from them, that solve problems they have never encountered rather than waiting for circumstances to return to familiar ground. Flexibility, in a parrot's life, is the difference between decades and years. Cognitive neuroscience has arrived at a consistent finding across the last 2 decades of research. The brain does not preserve capacity that goes unchallenged. Neural pathways that sit unused begin to thin. Myelin sheaths that speed signal transmission degrade when the signals stop coming. This is measurable at a structural level, visible in brain imaging, quantifiable in longitudinal studies. The people who maintain the sharpest cognitive function across a lifetime are those who keep exposing themselves to genuinely new problems, new skills, and new domains that force their brains to build new connections rather than run existing ones. They kept activating the loop. They kept behaving in the language of the research, like a parrot. Alex died on the night of the 6th of September 2007. He was 31 years old. That morning, at the end of his final session with Pepperberg, he said what he said every evening when she left. "You be good. I love you. I'll see you tomorrow." He had spoken those words hundreds of times. And across 30 years of working alongside him, Pepperberg had watched him continue building new objects, new concepts, new associations added to his understanding right up to the end. He never reached a point where he decided he knew enough. He never treated the world as a place that had already revealed everything worth knowing. The question worth sitting with is when you last did the same, genuinely went after something you did not understand. Asked the question you were uncertain whether you were qualified to ask. Picked up the problem and worked it from the beginning with no guarantee of where it would end. The capacity for that has not left. It was built into you before memory began, sharpened through a childhood you can only partially recall, and it has been running quietly underneath everything you have done since waiting for the signal to activate, for the loop to be fed, for the shell region to be given something worth processing. The bird in that Auckland laboratory did not pass the test because it was born different. It solved it because nothing had ever taught it to stop. Every day, it woke up inside an environment full of problems it had never seen before. And it approached them the way it had always approached everything, with the full weight of a mind that had never been told it was finished growing. That is the thing parrots carry that most creatures lose. The assumption that the world still has something to teach them. That assumption, held and acted on across an entire lifetime, is what turns a brain into something extraordinary.